In my last video, we discussed an observation from high altitude. Here's a quick recap. Getting as close to the water as possible maximizes the variability caused by refraction. This is the Bear Peak webcam from which we can see peaks over 90 miles away. At this altitude, there is no measurable change in these photos. Meteorological data from a local weather balloon station confirms that this is what we expect based on empirically determined equations for refractive index. Using the same formulas, we determined that we should observe distant targets slightly higher than they actually are. Can we use these photos to determine the shape of the Earth? If the Earth is flat, objects should appear to shrink as they move into the distance, in accordance with perspective. If the Earth is a globe, objects should also appear to shrink while sinking down in accordance with a physical curvature. Let's start with a physical model to ensure perspective is properly factored into our analysis, and then we can move on to computer models. I modeled the observation in 1 to 160,000 scale in units of inches. Starting with a straight line representing a flat Earth, I located the peaks at each distance. The peaks were cut out to scale, and the camera height was also marked with its eye level. I calculated the physical curvature drop according to this formula, which very nearly matches the common 8 inches per mile squared at these distances. With these numbers, I drew out the curved surface representing sea level on a globe. The cell phone camera is moved into position, and we're simulating what the camera on top of Bear Mountain sees, while being able to manipulate the shape of the Earth. To do a proper comparison, we need to scale the camera and model photos. Panorama Generator displays the headings which we can use to overlay this grid. If you do this yourself, make sure to set the vertical exaggeration to 1. Each grid cell is 1 degree, which is close to the size of your pinky finger at arm's length. To scale the model photo, I've used the angular size of the distance between these two peaks of the Bolivian mountains. Now we can line these photos up. The scale model with the peaks dropping away with curvature matches closely. The model of the flat Earth does not seem to match at all. Let's confirm this. If I model the nearest and farthest peaks in Walter Bislin's advanced curvature calculator, again the globe model matches, while the flat Earth model comes in much too high. Panorama Generator matches with the peaks almost perfectly, and it also is a model of the globe, with refraction that matches what we determined before,